Hello everyone, let's look at LeetCode problem number 1915, number of wonderful substrings. So this is an interesting problem. What we have to do here is that we are given a string. Example here is ABA, and we have to find the wonderful substrings. Now how a wonderful substring is defined? So a string is wonderful if and only if at most one letter appears an odd number of times. So what does this means is that in the substring either there is one odd occurring number and rest even, or we have all even occurring number. Okay, so let's see this example ABA. So let's first see all the possible substrings. So of length 1 will be A, B and A. Also we have to consider the repeating substrings distinct, so we have to count them again. So we will also have to consider the same substrings if they are repeating. Now of length 2 AB and BA, and the third one will be ABA. So in this we have A, which is a single character and it is odd times as it is one time. B, it is one time, so B is the only character and it is occurring an odd number of time. Okay, A is the one character and it is occurring odd number of times, so we will accept these. But for AB and BA we have now two characters and both of them appears all the time. A is also one time, B is also one time, and here also B is one time and A is one time. So what this violates a condition that it has two odd occurring number. Okay, we don't want that. We want that if there is a number which is occurring now odd times, so such numbers should only be one in a substring. So we won't accept these strings. And finally ABA, here we have A appears even times and B appears odd times, and in this substring we have only B which is occurring odd times and A is occurring even times. So we have at most one letter, that is B, that appears odd number of times. So we will accept this. So 4 will be our output, 1 2 3 4, and that's what mentioned in the example also. So now how will we solve this problem? We can solve this problem using prefix sum and bit masking. If you don't know bit masking, I will try to explain a little bit bit masking also in this problem. I actually tried to solve it without bit masking, but it was giving time limit exceeded. So yeah, let's move on to the approach of this problem. So the first approach that should come to your mind is that we generate all the possible substrings and we see if the substring is wonderful or not. So for generating all the strings we would require n square complexity, and for checking each string that is wonderful or not, what we'll do is we will make a map that will have the count of the characters for that substring, and so that we can see which number is occurring odd number of times. So that will also require, for each substring we will also require n time complexity more, so total will be, or that will be O of n cube. You can reduce this by n cube to n square. How? As we move the second loop, we, instead of starting the substring from I and j, what we do while moving j, we maintain a array. Okay, so we will look that in some next questions. So now, but this would give us time limit exceeded. Even n square or n cube, this will be time limit exceeded because the constraint given for n is 10 to the power 5. So n square will go 10 to the power 8. That will be exceeding the time limit. So that won't give us a solution. So now what we can do here is we have to have, what we can think of is that we need the count, or we can say we need the frequency of the characters. Okay, so what we need here is frequency of the characters. Why frequency? Frequency to know odd or even occurrences. Okay, if we don't know the frequency, then we cannot determine which number is coming odd times or even times. Okay, so yeah, we will kind of need to use a map here. And also one key thing to notice here is that the word or the string that we are given here is contains only letters from A to J, small a to small j. So these are only 10 letters. So we can denote any substring by a vector of 10, of size 10. So we can denote any of the substring by a vector of size 10. So yeah, And if we look closely, then we don't need the actual count of characters. What do I mean by this is that we only need to know if the occurrence is odd number of time or even number of time. So what we can do is we can represent this vector using parity. Or basically what I mean by this, let's say we denote an odd number by 1, and even number by 0. So what this means is that if a number is occurring odd time, so we will put a character is occurring odd number of time in the string, we will put 1, and if it is occurring even number of time, we will put 0. Okay, so what I mean by this is that we can represent any string using such representation where the count is represented by either 1 or 0, signifying odd and even. So let's take an example: A, B, C, D, E, 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 F, and G. Okay, so how will we now let's not focus on if the string is wonderful or not. We are just looking at its representation. So here A comes twice, so which is even time, so we will put here 0, and B come once, so that is odd, so we'll put 1. C and D also comes one time, so that will be odd. E comes even time, so that would be 0. F and G also comes once, so they will be odd, and rest are not present, so they are as good as 0 because they are not present. Now now let's take example of a wonderful string. How would a wonderful string look like? A wonderful string, what will a wonderful string have is, a wonderful string will have either one character occurring odd times and rest even, else what will have, all will be even numbers. Okay, so what does this means is that this representation will look like it will have only 1 1. Okay, what I mean by this, there will be only 1 1 in the representation, and all will be 0, and in this case, this was for this case, all the entries would be 0. So that will be a valid substring. Okay, so how many such representations are possible? If you look closely, that the size of this representation is fixed to be 10. Okay, one representation is where all are 0, and second case is that one of the character is odd. What does this means? This means that at one position there will be 1, rest 0. So we will have only this will be only one representation, and for every place, if we place 1 and rest will be 0, so we can have at max 10 representations. So total we have 11 such possible representations for a wonderful string. So these will be the 11 possible representation of the wonderful string. Now what we will do is assume that this is the word that we are given. It has characters, can be anything. This is not the representation but the input word, and so we will traverse it from this direction, and for each I, okay, this will go till the length of word. Okay, so for each I we will store its representation. Okay, what does this means is, let's say here it is A. Okay, so for A our representation would be at 0 index, it would be 1, so this would be our representation for A. So for I is equals to 0, we will store this whole array. Okay, for I is equals to 0, we will store this whole array. And yeah, for let's say we have now again A. For again A, now what happened is that frequency of A has become even and rest all are 0, so our all will be 0. And now so for I is equals, for next side, that is I is equals to 1, our representation will becomes like this. Okay, so let's say this is what we have stored for I is equals to 0. Okay, let's mark it on this side. This is I is equals to 0, this is for I is equals to 1. Okay, now we move further, and let's say B occurs. Okay, now if B occurs, then our situation is that count of B is odd. Okay, so count of B is odd in this case, so this is for I is equals to 2. Let's also mark A, B, C, D, so it would be easier for us. A, B, C, D, E, F, G, H, I, N, J. Okay, now let's continue with the dry run. So now let's say that we have C, and for C what we get here is, this is actually, we won't find a representation in these 11 state, so we will have to make a next state, because if we look closely, this is not a wonderful string, because it has now B and C, and both of them are occurring once. So what we'll do is, we will make a new representation for it, in which we will put 1 at the position of C and B, and rest will be 0. Okay, so for B and C we will put 1, so let's mark it with blue color only. For B and C, okay, no, this is not B, this is B. B and C we put 1 and rest will be 0. So this is for our I is equals to 3. And now let's say that we again have B. Okay, so if we have B here, then our representation should change now, because B is now occurring even times. Okay, so what we will see here is, we will see the state of the previous I. Okay, it's like prefix sum. This is what I was talking about, prefix sum. That as in prefix sum, you pre-compute it and add this value to this value and then this value, so that's like cumulative sum of these values. Similarly, for getting representations at each index, what we are doing is, from the previous index we are adding the current character, incrementing it. So if, let's say, it was odd previously, and so now it would become even, and if it was even before, so now it will become odd. So what this means is that we are just flipping the values from 1 to 0 and 0 to 1 for the character that is encountered. Okay, so now B is encountered. So if B is encountered, so our new state would be, this B will be flipped to 0, and if we look here, we have this as a valid string, so it is present in our 11 states. So we will mark it as 4 here. Sorry, this is for I is equals to 4. Now for next character, let's say we have B here again. Okay, if B here is again encountered, then again we will have this same state. Okay, so this will be same for I is equals to 3 as well as I is equals to 5. Okay, this is 5. And now for 7, let's say we have B again, or let's say now we have C. So now I hope you are understanding that now B is odd, and we will flip this bit and we will get only this one again. So this same representation 2 would come here for 6. Okay, for 6. Okay, this is 6, not 7. So for 6. Now yeah, let's just stop here. Now we'll have the string, and we will do this for each of the index. So for each of the index, we are storing the vector itself, the vector representation, this itself. Okay, and how can we do that? We can do that by making a map of vector of int, and let's say count. Okay, I will count, that is int. I will tell you why this int is here, why are we basically counting these representations. Okay, so now first let's see how can we represent them more efficiently. Instead of using this vector, this can be represented as a single number. Now you may ask how. This is actually pretty easy, because if you look closely to this vector or any other representation, any of this representation, it's only ones and zeros, and this can be uniquely represented by a number. Okay, for example, all of these are 0, so that will be 0. I wanted to look at it as in terms of the binary representations. Okay, now that we will have a 2 to the power 0, 1, 2, 3 up 9, so that is 2 to the power 9, will be represented by 2 to the power 9. Okay, now it would represent 2 to the power 8, 2 to the power 7, 2 to the power 6, 2 to the power 5, 2 to the power 4, 2 to the power 3, that is nothing but 8. This is by 4, 2, and this will be represented by 1. Okay, so now we can see that we can represent this whole representation as a single number. So instead of making a vector of int, you can now just make a map of int comma int. Okay, so this is where we are using the bitmasking, and this I have tried not using that and using the vector of bool for just marking true and false value for 0 and 1, but that wouldn't pass all the test cases, so you will have to use this bitmasking here. Okay, so now let's see why are we doing all this. Till now what we have done is, we have seen the representation, representation, and we have seen that we will maintain a map of like up to every index, up to like this. If this is our array, for each I we will maintain the representation which comprises of the all the occurrences of characters before it in a vector. And what I mean by that vector is that it will be representing the odd numbers in it by 1 and even by 0, because we don't need to have the exact count. Okay, so now why are we doing all this? So let's say that you have an array and you are at some index I. Okay, so you are at some index I, and now what you have maintained is you have maintained the vector or the cumulative vector at each I. Okay, so now for this I, let's say you want to find out, what you want to find out is the number of wonderful substring at ending at I. That's important, ending at I. Okay, so we want to find out the number of substrings which are ending at I. Okay, so for now just imagine that for before I, okay, for these indexes you have the answers. Okay, so what you have is you have answer for that. Okay, number of substrings ending at this I, number of substrings ending at some this I, and for this I. Okay, so what this means is that you have this answer for this I, for this I, and for this I. Now to find the answer for this I, we need to have it, we want to find out the number of beautiful substrings. Okay, sorry, wonderful substrings. Okay, so now let's say our current vector has like all even numbers. Okay, so if it has all even numbers, so how will the vector look like? It will look like 3 4 5 6 7 8 9 10, all will be 0 in the vector. Okay, and we have this vector also, it is also ended, it has also zeros, 1 2 3 4 5, 1 2 3 4 5, so it also has even characters. Okay, so now look really closely. Okay, for up to this I, some I which is here, we have this cumulative vector, and similarly for this whole I. Okay, for this complete from starting to here, we're maintaining the cumulative from starting. Okay, from this I also we have this vector. Okay, so what we can think of it as, we can think of the string in between this. Okay, the substring in between this. So how can we find out is if we subtract it. Okay, if we the occurrences of characters from here to here, if we subtract it, we what by subtracting we are doing is reducing the count. So if that was, let's say, even, so even minus even will remain even. Okay, even minus odd will give us odd, and odd minus odd will give us even. Okay, so what we are going to do is we are just looking at, we know that the occurrences are even or odd. Okay, zeros or ones, and if we know that if we subtract it, so here all are even and here also all are even. So if we subtract it, we will again get a vector which is even. Okay, so all are even, and for this substring we have occurrences now in which all are even. So if all are even, this means that this is also a wonderful substring, because all are even. Okay, so now I hope you have understood that why is this we are finding as a wonderful substring, because the substring ending at this index had the same representation at this one, and when we will subtract it, we'll get 0. And now this is not for 0. For example, if it had any if at this I we would have had any of the representation, let's say instead of this we had something like 0 1 1 0 0 0 2 3 4 5 6 7 8 9 10. Okay, so now we can see that this is not a wonderful substring. This is not a wonderful substring, but this is not the substring, this is a substring which is starting from here to here. Okay, which is starting from 0 and it's represented up to here. Okay, so now what, let's say that for this I, this particular I here, we have the same substring as this one. Okay, this is the same substring as here. So now what we have is that from here to here we have a same substring. It is not wonderful substring, but it is the same substring, or we can say it is the same cumulative sum. Also here also we had find out that it is the same substring. So what we will do is we will see this now, because if the vectors are same, when we will subtract it, okay, what this means is the respective count of each character up to that I is same. By same, I don't mean the absolute value, either the even or odd. Okay, so if we subtract it, we will get 0 0 0 0. Okay, what we'll get is we will get 0 0 0 0 only. Okay, because if those are same, so odd minus odd will also give us even, and if both are same and even, so even minus even will also give us even, so that will be 0 0 0 0 0 10 times. Okay, so we will again get this a wonderful substring, wonderful substring. Okay, so now till now what we have seen is that if for this any array at index I, in the previous indexes, if we find the same representation, if this representation and this representation is same, there may be multiple same occurrences of like sequence also, because if here it is, then here it can also be the same, and ending at this index and this index we might have the same representation. Okay, so now up to I we also have same representation. So what we have seen that if we subtract it, we will get 0 0 0 0 0 0 0 here signifies all even. So this means that we have this substring in which all are even, all are even, in this also all are even. So how many wonderful substrings did you find? How many wonderful substring you find? That is 2. Why 2? Because you have two same representations before. If you have two same representations before, you will get that many number of wonderful substrings, because subtracting those will give us 0 0 0, so all will be even. Okay, so we have covered one case, that is all are even. So for all are even, for finding this wonderful substring, we have to find the same representation. Okay, so now how would we find out for the other representations, that is if one of them is odd? How can we do that? Okay, so for finding out if one of them is odd or not, what we were doing is we were now subtracting the same representation. Okay, but what if we alter one of the index at a time? Okay, so if our representation was 0 0 0 0 0 0 0 0 0 0, okay, and this was our representation, let's say at I, for any I, if this is our array, and for this I we have found the cumulative vector, this one. Okay, this one, not this one, we have one odd. Okay, so it's not necessary to have odd here. What I mean to say is, if we find the same vector, if we find the same representation, then this will give us all even string, all even, that will work. Okay, but now let's say what we find in this string is, now if this is not same, this is not 0 0 0 0, we find a string which is altered just by one of the index. So let's say we have 0 0 0 1 0 0 0 0 0 0. Okay, so now if we look closely, that we have a difference of only one character. So now if we subtract them, what will happen? We won't get all zeros. Instead, what we'll get is, at this position it will be 1. Okay, and this is also a valid representation. This is one of those 11 representations which we saw. So this is also a valid representation. So if we found a vector which is altered only at one of the index, so their subtraction will give us a sub vector something like this. Okay, which is a wonderful substring. So this won't be all even, this would be about odd substring, odd wonderful substring. Okay, and we can have multiple such representations. Like here, if we had something like again the same vector, or if we had like 0 0 0 0, and again it's getting 1 at some point. Okay, so what you understand here is, by subtracting this vector from the vector till here, if we get a vector which is like if we find a vector I previously such that which is altered only by one of the index, so we can do that. Okay, so but which index do we find? We have to find for all index. That's why in the question we are given only 10 possible values in the of the characters, because then we can represent the count in a vector of 10. And what we'll do is, we will make a for loop, and in the for loop what we will do is, for the current vector we will change this to 1 by 1. First we will change this to 1. Let's take another example so you understand it better. So now if this is our vector, and a substring is ending here at I. Okay, and it looks something like anything. Don't this representation need not to be a wonderful substring. So let's say this is what we found is 0 1 1 0 1 0 0 0 9 and 10. Okay, so this is not a beautiful this is not a wonderful substring. Okay, and what we do is first for even number we will check if the same cumulative vector has appeared before at any of the previous i's. Okay, so first we will check for the same vector. If we find the same vector, then this we will add its count, because this will be a all even substring. So we will have to add number of such same occurrences. If there are multiple, so we'll add their count. Okay, so what we have to maintain now is, in the map we have to maintain also the count of such representations before. So this was representation, so it count would be 3 in the map. Okay, for this substring, if we have found the same same representation before, so we'll update its count, so that would be 3 now. And if we find again here that representation, so what we'll do, we will say that okay, there are 3 of these, so every this substring, and this substring, all these 3 substrings would be a wonderful substring. So we will have to add the count of them in the answer, so all even would be 3. And now what we do here is, first we will now we will alter one character every time. Okay, so now we will do 1, we are flipping this character, so rest will be same. And we will see if we find this vector now. If we find this vector before, then what this will give us, this will find us another vector. Okay, and if this altered character is found, okay, we are altering this. Okay, we are altering this and getting this, but our original vector till here now was this only. And since we are altering just one character, so if we find this one here, so what this means is that this whole, that is this minus this, will have a difference of any one character at any of the representations. Okay, so if that happens, so we know that this is a valid wonderful substring, because it will have only one odd occurrence character. Okay, so for this we will alter this character and see if we find that. Then we will alter the second character, so we will do 0 0 1 1 0 1 0 0 0 0 0. Okay, then we will again see how many occurrences of such sequences are there, and that minus this representation will have anywhere a difference of 1. Okay, and that is where, that if you look closely, then if you find this number there, so our change in the character would be here only. Okay, because we have altered it and we found that, and this character would not be present in this representation. Okay, so now what you have understood is, what you have to do mainly here is, you have to do 2 things. You have to maintain a vector representation, a cumulative vector representation that would update itself with each i. What you will do is, you will maintain the representation. Okay, and second thing what you have to do is, you have to maintain a map which would use this vector, the representation vector, and its count. So that would be in vector comma count. And now what we are using here is kind of prefix sum. Okay, but you should know that this vector, as we have understood, it's just zeros and ones, and this can be represented by a number, a binary number. So this is where bit masking comes into picture. If you have understood this now, you don't need to apply the bit masking. What I would suggest is, in the code description, I have mentioned the LeetCode solution. In the LeetCode solution, you will find 2 codes. Okay, one is that is not commented, that is the bit masking solution, and that will submit. Okay, that will get submit if it is using bit masking. And there is a second code which is commented. Okay, so the commented part is using this vector. Okay, why using this vector? Because using this vector you will understand it better. Okay, so using this vector you will understand it better, and but the thing is that it won't submit, because the vector is solution is slightly inefficient, so it won't pass all the test cases. Okay, so if you want to understand it, you should see this commented code, and then later continue this video to understand this, not the bit masking solution. Okay, So if you know bitmasking, you can jump directly here, but if you don't know, I would suggest you going that. And I think the bitmasking used in this problem is fairly easy. Okay, the only thing that makes this question a little bit interesting is that it's using two concepts, using of bitmasking also and prefix sum also. Okay, so now what we are going to do is, let's see a dry run. Okay, let's see a dry run. So let's see that if we have a string something like a b c. Okay, so how will we find the wonderful substrings for this? Okay, so first, according to our logic, we will go. So first we will make this I. For this I, we will check the previous i's, and if those the count of okay, so now first let's make the vector. Okay, so let's say our vector is vec, and first it was uh, 0 0 0 0 0 0 0 0 0 0. Okay, this is initially what our vector was, because there is no character, so all are as good as even or 0. Okay, so now for I is equals to 0, this is 0 1 2 3. What we find the representation is that we have find the character a, so we will do this one 0 0 0 0 0 0 0 0 0. Okay, so now this 5 and 5. Okay, so we have found this representation. Now for I is equals to 0, we will check now two cases. Okay, we will check now two cases. The case one is for even, for even occurrences. We will check previous to it if we find the same representation. So till now in the map we have nothing, so we won't find any same representation. Okay, now we will see for altering one of the character. Okay, so we will alter one of its characters. So let's say first we altered this 0 0 0. So this will be altered and we will get 0. We'll get this representation and we'll find its count. This is also 0. So now look there, this is one of the edge case, that if we look at this, this is a single substring. Okay, this is a single character, and a single character will be a wonderful substring. Okay, so how can we deal with that is, because we are looking at the previous we are looking at the previously stored count of such representations. So there is no count of this, there is no count of this. Okay, so what we need to do for this is, in the map, what we'll do is, let's make a separate region for map, because the map will store vectors. Okay, so now for this map we will have, for this map we will initialize that this count of this 0 0 0 is 1. Okay, now why, because when this is altered to this, we will find that okay, this is existing in the map. Okay, so count of this is map and its count, this is key and this is count. So now count is 1, so we will add the count in the result vector, in the result variable. So now we have gotten as a result 1 from here. Okay, so let's make it with yellow. So we have gotten 1 here. Now what we have to do is, we found this vector now, so we will have to add it to the current to the map also. Okay, so this vector, as we have found ending at this I, we have found this cumulative vector, so we'll have to add it in the map as well. So it will be 1 and its count also is 1. Okay, we have increased the count. Okay, now for I is equals to 1, for I is equals to 1, for I is equals to 1, first we'll find the next vector. So in the previous vector, what we are going to add is the we are going to add the count of current found character. Current found character is a, it is already 1, means it was odd. So if we found 1, odd plus 1 will give us even, so that will become 0 0. Now what we will do is, we will again see the two cases. Case 1 for even occurrences. For even occurrences, what you find is the same vector previously. This same vector is present in the map. Okay, this same vector is present in the map as its count is 1. So we will add 1 into our result. Okay, and now again we will go for second one. We will alter one of its character every time. So first we will alter this character. Okay, here also you will alter all the other characters, but in the map you won't find any occurrences of them. Okay, so the count from them will be 0 only. Okay, so even occurrences, we found that okay, it has same vector 1, and now we alter this, we get 1 and rest all zeros. and for such vector we also have count 1. So again we will have to add 1 here. Okay. Now what we will do is we will go for I is equals to 2. Okay, let's just adjust it here only, because then we'll have to scroll a lot. Okay, so this was for I is equals to 1. And now if you alter any of the other character one by one, if you alter this character one, this character, this character, this character, you won't find any of the occurrences. So this will be 1 only. Okay, so this we are left with 1 1 count only. And now we will go to next I. So our next I is I is equals to 2. For I is equals to 2, we will add this b to our current vector. So this was our current vector. Okay, so now it will 0, and count of b is represented by here, so 1, and rest all will be 0. All these will be 0. I think there are extra zeros in this one. Yeah, let's remove them. And now we will again look at two cases. Case 1 of even occurrences, case 2 for odd occurrences. If we find the same vector, we don't find the same. Okay, first thing to remember is that here also we found 0 0 0 0 again, so we'll have to increase its count to 2. Okay, so we'll increase its count to 2. Okay, and now after finding the count for that, we will increase count for that particular vector also. Now for even, if we look at the map, we don't find anything like this, so this will give us 0 only. And for odd we will alter one of its character at each time. When we alter this, we won't find a string. Okay, when we will alter this, we will find a string, that is this one, and its count is 2. Okay, and its count is 2. So now what will be added is 2. Okay, its count will be added 2. And now we will move to I is equals to 3. Okay, because later if you alter any of the character, you won't find any occurrence. Okay, so now we will move to I is equals to 3. For I is equals to 3, the vector will become 0 1, and again 1, 0 0 0 0 0 0 0. Okay, now it becomes again 1 for this C. And if we again look at both the cases for even, so we won't find any of this string. Okay, and also here, as you found 0 1, so you will have to increment, make the entry for this one also, because it doesn't exist in the map. So it will be 0 1, and rest will be zeros, and you will find the count of this as 1, because for I is equals to 2, you found this cumulative vector. Okay, so you will store that. And for again, if we look at even, this will give us 0. And for odd, if we alter character one by one, if we alter this, we won't find any occurrences. If we alter this, so that will be 0 0 1, and there's no occurrence of that. But if you alter this one, you will have 0 1, and rest all will be 0. And we have this 0 1, and rest all are 0, and its count is 1. So what will be added in the answer is 1. Okay, now let's see how many wonderful substrings we have found. So we have found 1 plus 2 3, and 3 and 3 6. We have found 6 wonderful substrings if we sum up the results. And now let's confirm this. If we had the string as a b c, okay, if we had this string, so what are the possible substrings of length 1 a, b and c of length 2 a, ab and bc of length 3 b, and for again length 3 is abc, and length 4 will be the whole string abc. Okay, so now this is valid, this is valid, this is valid, this is valid, because there is only one odd number. This is valid because both are even. This is not valid, and this is not valid because both are odd. Again we see that this is also valid. Okay, because this occurs even number of times, and only this occurs once odd. In this, all characters are odd, so this is definitely not valid. This is even, but both b and c are occurring odd times, so this is also not valid. So if we look at the count, 4 and 2, that is 6, and that is what we have gotten our answer. Okay, see the code. This is the using the bit masking. So this is the map. It is nothing but what we have discussed is it stores the count of previous cumulative vectors or representations. Okay, and now this mask is nothing but the current vector which we initialized it by 0. Okay, so it's nothing but the vector representation to represent at any index I of the array, where are we. Okay, so it just represents the cumulative frequency up to that. So initially that would be 0. Okay, and m of mask of 0 is equals to 1. What does this means is, m of mask is equals to 1 is means that for the vector 0 0 0 0 0 0, this is represented by nothing but 0. So we have done its mask, which is initially 0 now to 1. We have discussed that for this single characters starting, we have to have this 0 to count them, as we are just looking at the previous, we are finding the current answer based on the previous one. So this is nothing but, this is like our base case. This is like our base case. Okay, and now we will have this answer. This answer is nothing but the result that we have used to store the final answer. And now in this loop we will traverse the array, and for this, what we are doing here is, in this index variable we are getting the character whose count is to be updated. For example, if this was our vector 0 0 1 0 0 0 0 0 0 0, okay, so, and if we have now, let's say we have encountered d here. Okay, so now we know that this is represented by this index. Okay, so in the vector, if this was a vector, so how would we have done that? We would have done that vector of this current character, that is d minus a, and now this d is represented by this c because we are iterating the array. So we will, in the code, we would write vec of this c minus a plus plus, or we should say is equals to flip this. So how can we flip this is, if we represented it by boolean vector, so we would have done this is not vector c minus a. Okay, so that's how we would have flipped it. But now this is represented by a mask. Okay, and so now this is what we would have done in the vector, but now this is a mask. Okay, so our, let's say this was our current mask, so it would be 2 to the power 2, as it's 0 0 and 1. So 2 to the power 2, that will be represented by 4. So we now only have a number. How can we update this with the current thing? So what we'll do is, we will take this one, okay, and shift it index times. Index is nothing but the this representation or the index in vector, so that we will find by character minus a. Okay, so we have find out the index. So now that's coming to be 0 1 2 3. Okay, so we will shift it 3 times. Okay, so we will shift this one 3 times, left shift this one 3 times. So what will happen is, this will become 0 0 and 0, because it is shifted once, twice and thrice. So this is what we have found. And now we have reached this one, and rest would be 0. After shifting this, rest would be 0, and we can assume that in front of it is also 0. And now what we'll do is, we need to add at this index our current vector. Okay, so we don't need to actually add it, we can take an XOR. Now why XOR? Okay, because if this was our previous one, so XOR, what XOR does is, if those are same, so this would give us 0, and if this is different, then this would give us 1. Okay, so similarly, what we did was, if we would have found out again, this has c character, it says that c is occurring once, and now if we have find that our current c is nothing but c, so what would c minus a will give us? C minus a will give us 2. Okay, so we will shift 1 by 2 to get this one at the correct position. So when we'll do that, we will again get this one, and our initial representation was also this one. Okay, so what vector will we get? This will same, so 0, this will same. Now this is also same, so this is 0. So what XOR is doing is, XOR is doing same thing for us. If it's 1 and 1, so it will do it 0, as it should, because both are odd, so odd plus odd will become even. If both are even, so that would be even. But if 1 is odd and 1 is even, in these cases 0 or 1, it will give us 1 1. Okay, so that's what we would use. That's why we would use XOR. So what we did was, we shifted this one by index to get this one to correct position, and we added this, we XORed this to our current mask to get the current representation. Okay, so now when we get this, this is our case 1. Case 1 was, what was case 1? Case 1 was finding this same mask previous to I. Okay, count of this same mask previous to I. Okay, so we will see that in map, do we have an entry for the same mask? If we have it, we will add this count into our answer. Okay, and this whole is nothing but our case 2. In case 2, what we are doing is, for I going from 0 from 10, okay, we are what we are doing is, we are shifting this 1 to I times. Okay, so what will happen here is, let's say that for I is equals to 0, how many times are a will be shifted? For 1 will be shifted, 1 will be shifted 0 times. Okay, Now for I is equals to 1, this would be shifted like this. For I is equals to 2, it would be shifted like this, 0 0 1. For I is equals to 3, 0 0 0 1. Okay, so and when we will XOR this with our current mask, when we will XOR this with our current mask each time, what will this do? It will alter one of its character at the ith position. So this is what it is doing. It is altering one of its character, and then we are storing that as this number as pre-mask, and we are checking that okay, now we have the same number of occurrences of the pre-mask itself, and we are adding it to our number. And when we find that number, we will add it to our result or answer. And finally, what we have to do is we have to increase the current mask, that is this mask that we find out, this mask that we find out for current vector, we have to increase its count as well. Okay, so I really tried to make you understand this problem. It was using some concept, so it was kind of difficult. So I hope that you got this problem and tried to explain everything that I could. Okay, so thank you. Tell me if you like the explanation or you expected something more. Okay, thank you. Bye bye.
Goodbye. 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 Goodbye.